Welcome to lecture 14 of Risk Management and Insurance. In this lecture, we will use some rules, on expectations that I have put in the appendix. Let's assume we have two random variables, x1 and x2, and two constants, a and b. So the expected value of the constant a is a itself. The expected value of a constant is the constant itself. Actually, I used this rule before. Now, the expected value of a random variable times a constant, you are allowed to factor out the constant. Okay, those are very well-known rules. Now, if I have here a sum of two weighted random variables with a and b, the constant weights, then actually you can write the expectation to each random variable and bring the a, the constant, in front of the expectations. So that will become important when we calculate the expected return of some share portfolio. You see, it's here you have the entire share portfolio, share 1, share 2, A and B, that's just the numbers of shares that you buy of each share. And then you can actually calculate the expected return, x1, x2, you can calculate it by taking the expected return of share 1 times A plus the expected return of share 2 times its weight in the portfolio. So then, the expectation of a product, it's actually, you can write the expectation to each random variable, and don't forget the covariance. Now, if the random variables are independent, then naturally the covariance will be 0, and then you have just a product here of expectations. But in general, the random variables will not be independent, so you have to use also the covariance here. Now, let's do those rules for the variances. The variance of a constant is naturally 0. Okay, the constant does not change, so the variance is surely 0. Now, if you have a random variable times a constant, the variance of it, again, you can actually write the constant before it, but you must square it. That's shown in statistics classes. Now, if you think here about the variance of a portfolio return, maybe that's return of share 1, the return of share B, and then you have here the weights. That it looks like this. So weights square, you write the variance to each random variable, but you must square the weights. And again, you should not forget the covariance times AB. So the weights also appear here, and times 2. Again, if those random variables are independent, then actually this covariance is 0, and you have here a somewhat simpler expression. Now, if it's not addition, if it's a minus here, you still have the plus here, and the minus only goes here. Now, the variance of a product, that's more complicated, and I will not discuss it here. The expected value of a product of random variables, that's actually still relatively easy. But the variance of a product of variance, that's actually more difficult. And we don't need it. Those rules I will use in today's lecture. So the rules were in the appendix to the chapter. Now let's turn to absolute and relative risk aversion. And we now go back actually to a situation where the risky prospect involves positive and negative shocks. So it's not like what we did in the last lecture, where you either had a 0 loss or a negative loss. Here you can actually have again a gain, or you may lose. So that's what we did earlier. And let's do it in a way, so the expected loss is actually now again 0. in the previous chapter, the expected loss was negative. But this will make it, this assumption will make it a bit simpler. So we have, again, the situation of the fair game. The expected wealth is actually equal initial wealth. You don't expect to lose or to make a profit. What's new is actually that the findings in this section hold now for any probability distribution, and not just for the binary prospects that we discussed, okay, in the last lecture. So we will be more general here. Now, the expected utility without insurance is now like this. Now, this equation replaces equation 16 from before, the expected utility. You see, we no longer have here a binary prospect, so with 2% chance, and we have actually a loss, and with 98% chance, we have no loss, and we write down the expected value. Okay, that we cannot do here because we no longer have a binary distribution. We want to be more general. So what we do here applies to any probability distribution. And so we simply write here, okay, we have the wealth plus a random variable, which is a loss. It could also be now again a gain. Okay, its expected value is 0. And we take the utility of our initial wealth plus the random variable of the sum of that. And of this utility, we want to take the expectation. Okay, so this goes to the right side of equation of the earlier equation 18. So here in equation 18, I just wrote expected utility, and because it was binary, actually we had this here, 16. Now we are more general now for as expected utility in 8. So it's no longer binary. So we just have here our wealth plus a random variable. We take the utility of it, and then we take the expectation. So that's the expected utility here. And we use this on the right side. So equation 25 stands now for equation 18. On the left side, we have the expected utility with insurance. And that's just, okay, the initial wealth minus, okay, the risk premium, okay, that we pay for insurance. The expected loss drops out because it's now 0. So it becomes a bit easier here. Let's go back to 18. You see here, it was W0 minus EX minus a fair premium minus rho. Now here actually the expected loss of fair premium just will be 0. And so I have just W0 minus rho. So EX is 0. So I just assume EX will be 0. So it no longer appears here. Okay, so that now replaces the equation 18. We can now again try to solve this equation here with regard to rho, with regard to the risk premium. But there is a problem here. You see, you cannot do it. You cannot solve it for rho in the same way as equation 18, because the expectation operator, you should not write it into the nonlinear function u. So that's actually because of Jensen's inequality, which is a topic that's actually also discussed, okay, in statistics classes. So you cannot write here actually E of u. You cannot write the E actually in here. You cannot write u of E. That would be wrong. That would be an error. And it's wrong, okay, because this utility function is actually nonlinear. Remember, it's concave because we are risk averse. Now, with linear functions, you are allowed to write the expectations into the functions. But with nonlinear functions, you're not allowed to do it. And that's because of the Jensen's inequality. So basically, we cannot invert, okay, this utility function here and solve for rho. Okay, that's and so we do on the right side, what we will do some Taylor series approximation. And also on the left side, left and right hand side, we take Taylor series approximations around the known initial value of wells W0. I take on the left side, I take a first order Taylor series expansion. So I have here initial wells, that's my utility. And then you subtract here the risk premium that the consumer is willing to pay for insurance, a rho. And so we move along the linear line and not along the curve. That's what you do in Taylor series expansions. It's a little bit funny that I do it here in the negative regions. Usually that's naturally explained, okay, with positive changes, and then you are somewhere here. But naturally you can also do it here with a negative change. So the risk premium is small relative to initial wells. So actually first Taylor approximation will be used here on the left-hand side. So utility after paying this risk premium, after reducing the wells by the risk premium, is just the initial utility out of initial wells times a rho, okay, times the first derivative here. And it's minus here, okay, because we go to the left side. So it's a utility, it's initial utility minus this red line here. And this red line here is just rho times u prime. So that's because if you divide the red line here divided by rho, you get here the tangent here of the, you get there the tangent, the first derivative. And so actually you can multiply the first derivative times rho and you get here the red line. You make a small error, but it's not too bad because you see the risk premium probably will be quite small. Maybe you have an invalse of $100,000 and so how much would you like to pay for insurance? Maybe $2,000. So actually we don't work with a big change here. And so we stick it with a first order Taylor series expansion. Now, the random variable x, how I can assume values that are much greater than rho. So the loss can be much greater than the insurance premium that you pay. You see your house may burn down and then actually basically maybe your entire wealth is wiped out. So you have a huge loss. So if you only take a first order expansion, because then you would have a big error here. So on the right side of the equation, we take a second order Taylor series expansion. And then later on, we also look for third and fourth order. But that will be a bit later on. So the risk premium is quite small. So that determines insurance premiums that you buy. Maybe that's 2% out of wealth. But if your house burns down, maybe your entire wealth is wiped out. So you have a big change here. And so you should not just move along the straight line. So we will do here now on the right side, we will do a second order Taylor series expansion. So you have here initial wells, then you have the first order term as before, and then you have here the second order term. And that's an approximation. Now let's take now expectations of it. You see that stuff here on the right side is linear. So I can now actually write the expectation of it, write the expectation to the first item, the expectation to the second item, and the expectation of to the third item. I can do this because I have just here plus signs. Now, the utility of initial wealth is constant. because initial wealth is constant. So the expected value of this term here is just a constant again. That's just a utility of initial wealth. If you take the expectation, because that's constant, actually the expectation does not matter. You do not have to write it down here. Here, in the second term, the expectation goes to the random variable. First, you have the expectation here. So you have the expectation here of a constant times a random variable. You see, this first order derivative is constant. It's just the rate of change of the utility function at the point of the initial wealth. So that's a constant here. It's a rate of change of the utility function at the initial wealth, and that's a constant. So we have here the expectation of a constant times a random variable, so you can actually factor out, bring the constant before the expectation. So I write here u prime times expected value of the random variable. Same thing here. The second derivative is naturally just again a constant. It's just the curvature at the point at initial wealth. So that's constant. So when you write the expectation here of the second term, you have so stuff is constant. So it goes actually here. The expectation. So it goes to the random variable. Again, the constant stuff you can factor out. That's those rules that we discussed just at the beginning. And now, okay, you have here, we have assumed that the expected loss is 0. So, okay, obviously we get here a 0. And so this entire middle term here drops out. And then because the expected loss is 0, then EX squared is actually equals the variance. EX squared just becomes a variance because the expected loss will be 0. Okay, that's something that you probably know from statistics classes. Let's try to write it out. Okay, even if it's a bit messy. Okay, here's a pointer. So you have the expected value. So I take the expectation of x minus EX so, and if you square that, that's becoming the variance. So variance is just the expected value of the x values of the deviations of the x value from the mean, from the expected value. But now naturally, if this here is 0, then then this becomes just expected. So you get just e of x squared. So that's what I'm using here. You see, e of x squared is just equal to the variance. And that's true because actually the mean is 0. This mean here is 0, so actually the variance is just EX squared. So variance is just EX squared because the mean is 0. But it's also important, so I can now write for this variance here, I can for EX square, I can just write the variance. And then I said before, EX is 0. Yeah, okay, so this middle term drops out. And so it simplifies to this. So that's 29. That's the approximation we have on the right side of the equation. So substitute now 26 and 29 into 25. Remember, we had here a problem in 25. Left side, right side. In 25, we cannot solve this because you cannot write the expectation into a nonlinear function. That's Jensen's rule. And so actually we take now on the left side, we take a first order Taylor approximation. It's only first order because actually this premium, this risk premium will be quite small relative to wealth. So a first order approximation is okay. Now, so loss really can be as big as the wealth, okay? You can be totally wiped out. So here on the right side, we take a second order approximation. Now we have those two terms now, we can plug them in here in 25. So we have the left side, we put this on the left side. We have this on the right side. We put that goes to the right side. So 26 and 20 now go into 25. And this you can solve for rho. Just rearrange and you will get rho. And then actually I will rename, okay, I just define, okay, the ratio of the second, the first derivative, I define this as the Arrow-Pratt coefficient of absolute risk aversion. Okay, so that's a neat equation for the risk premium of the consumer. What we have calculated here, this approximation is the approximation of that's the approximation of this, of the rho. Here you get the rho exactly. If you know the shape of this function, you can calculate the rho exactly. But I have now given you an approximation for this rho. For the risk premium. So in the tutorial, sometimes you have to calculate it exactly, or you have to use the approximation. The questions actually will tell you what you should do. So that's a very convenient approximation formula for the risk premium. So yeah, okay, here I just comment a bit. As a consumer's risk premium is approximately equal to 1/2 of the product of the variance of wealth. So the variance of wealth matters, that's the objective component. Okay, and the coefficient of absolute risk aversion, that's subjective. You see the coefficient of absolute risk aversion, here you have the first and the second derivative of the utility function. And this will be a little bit different for everybody, we said, the utility function. And so actually that's subjective. That reflects the taste, that reflects how strongly risk averse you are. Now, this variance here, that's also objective part. That's just the variance of the loss. Okay, so that's objective. So the behavior of people matters. Okay, it's a utility function which determines their behavior. And then also naturally objective risks matter, which you capture by the variance. Or you can say, okay, for a given risk, the consumer's risk premium is proportional to the coefficient of absolute risk aversion. Yes, that's also true. So for a given risk here, then the risk premium becomes proportional, okay, here to the coefficient of absolute risk aversion. Now, risk aversion, we said, depends on the concavity of the utility function. how strongly is it curved. But the second derivative is actually not sufficient. Okay. So you would actually say, okay, maybe why do we not just have only the second derivative here? Why do we divide by the first derivative? With the second derivative, that determines the concavity. But this actually will not work. And it's actually a topic that is discussed in microeconomics classes again. Okay. You see, the second derivative of the utility function does not provide a useful measure of risk aversion because it's not invariant to affine transformations, and also not invariant to linear transformations, but more correctly actually to affine transformations. Therefore, we divide the second derivative by the first derivative, and then you have, if you have a affine or a linear transformation, then actually the coefficient risk aversion will not change. So you can actually transform your utility function, and you will get actually the same rho. That's a topic, as I said, in microeconomics classes. Utility functions can be transformed, and you will still get the same behavior. Okay, that's if those transformations are actually affine. Now let's rewrite equation 31. Let's just divide by the wealth on both sides. So I have now the risk premium as proportion of wealth. You see, I divide the risk premium divided by wealth. So before, the risk premium actually was in dollar terms. Now let's divide the equation by wealth. So I have it on both sides below. I divide it by wealth here. I divide by wealth here. Yeah, okay, and then actually to get the square, at the same time also I divide again by wealth and I multiply by wealth. So I do two steps. I divide by wealth on both sides, and then I divide and I multiply wealth into it on top and below. So okay, I get here wealth squared. Now that's called the coefficient of relative risk aversion. Now this here, and here we express then actually the risk premium as a percentage of wealth. The risk premium is expressed as percentage of wealth. I have here the coefficient of relative risk aversion. Also actually the risk, the objective risk is actually expressed relative to wealth. Now what you have here is actually a squared coefficient of variation. This is a square coefficient of variation. Okay, that's what I explain. Okay, that's why I don't call it sigma, I call it sigma tile. Now the coefficient of relative risk aversion equals the coefficient of absolute risk aversion times wealth. That's certainly true. You see you have a relative risk aversion. Here you have the absolute risk aversion. It was just the ratio of the two derivatives, and so times wealth. Okay, so RA times wealth gives you a relative risk aversion. And as I said before, okay, also risk is expressed relative to wealth. So I have here sigma tile, which is the coefficient of variation of wealth. Now the coefficient of variation actually should be used more. You see, we usually use a standard deviation, but it would be better to use actually the coefficient of variation. Let's make an example. Let's assume you measure that the standard deviation of a share is $5. So that's a standard deviation. Is this a lot or is it not a lot? Okay, you can't say. It depends on the share price. If the share price is maybe $7, okay, then that's a huge standard deviation. But if the share price is $100, then that's a very low standard deviation. 5 out of 100. Yep. Let's do that again. 5. Let's assume the share price is 100. So if the share price is 100, then the standard deviation of 5 is naturally small. But if the share price is 7, a standard deviation of 5 is a lot. And so the standard deviations actually really don't tell you so much. You have to put it in relation to the variable that you're interested in. And okay, the coefficient of variation does this. So here I'm using actually the squared coefficient of variation. Okay, it's a sigma squared divided by Wells square. Okay, that's the lecture of today. Thank you.